Topic 12 is also the last chapter for this module. We will continue to discuss how to apply our upper bound theorem to a more complicated structures like a continuous beam and a rigid frame. Today's arrangement of this chapter, I will firstly discuss continuous beam, how to dealing with continuous beam using upper bound theorem, and then talk about frame structures with different configurations. Part 1 and Part 2 are more related to calculations. The third part is also some theory. What happens if you also consider shear force and axial force, the behavior of the plastic hinge due to different axial force and shear forces. The last part is some reference. The last part is some reference material, so-called yield-like network and Tripp's network. They are the extension of upper bound theorem to some airy element. Let's talk about the first one first, continuous beam. How to apply upper bound theorem on continuous beam? Continuous beam means a beam with more than one span. If we have one force acting at one particular span, then how to find out the maximum force, like here. If we have force acting along span CD, you can see that the effect of this force will also propagate to the remaining positions. And we would like to know how to find out the maximum force that will make the beam collapse. Well, for upper bound theorem, you may apply the same theory. Let's consider the failure mechanism. When the beam under one force in portion CD, most likely failure will occur in portion CD. Okay, there will be some bending moment along member AB and member BC, but they are not very critical because there's no any direct loading in this example. So we believe that portion CD will be our critical section. And then for this portion, there are only two plastic hinges. There are two plastic hinges in this portion. 2 degree static indeterminacy is degree 2. How to calculate static indeterminacy? Again, you have 1, 2, 3, 4 reactions. You have 4 reactions. We have 2 equilibrium equations, moment equilibrium and force equilibrium. We have 4 reactions, 2 equilibrium equations. 4 minus 2 tells you the degrees of indeterminacy. We have two unknowns more than the equations. Okay, the equation is not sufficient to solve the formulas. We call it static indeterminacy. The static indeterminacy is 2. That means you need totally something like 3 hinges right at most. But you can see that for portion CD collapse, there is only required 2 plastic hinges. One is at point C, the other one is at the middle. It seems that for this part collapse, there is only 2 hinges required. Okay. If you go back to the previous chapter 11, we mentioned that normally the hinge number is 1 more than degree of indeterminacy, right? That means 3. But that is not always true. That's not always true. N plus 1 is only the maximum value, maximum number of hinges. It's not tells you the exact number. Okay, not the exact number. That is also the reason why I'm not very often to use it, because they cannot tell me the exact number. It really depends on the scenario. Just like this scenario, after formation of 2 hinges, you can see this kind of failure mechanism. Point D is a rotor support. That means it's originally a hinge at point D. When the number of hinges is smaller than the expected value, we call this partial collapse. For continuous beam, it may somehow collapse due to partial mechanism or complete mechanism. So we have to try all scenarios. I think I showed you some other things before. If you have more than one possibility, then you have to try all possibility and find out the smallest value. That is the key things for this part. Try all combinations and then pick the minimum values to find that becomes your collapse law. So some concept. This just explains what I mentioned before. If you have n degrees of indeterminacy for structures, then not only is required n plus 1 plastic hinge to make the structure become unstable under plastic collapse mechanism. If the structure satisfies this requirement, then you call this complete mechanism, complete collapse mechanism. But just like the previous example, this is not always true, because sometimes, especially for frame structures, the number of hinges required for the structure collapse is less than the required number, n plus 1. For this scenario, we call that partial collapse. That means the hinge number is smaller than the expected value. Okay, this is quite often, especially when you're playing with some complex structures. Partial collapse. So maybe this expression n plus 1 may give you some idea about the maximum number of hinges, but it cannot tell you the exact values. The exact value, you have to use something like trial and error. You have to insert hinge yourself to see the actual situations. So do not totally rely on the formula. Sometimes they will mislead you. Maybe we can I can demonstrate how to play with continuous beam using one simple example. Example 1. Suppose we have a free-span continuous beam under 2 concentric forces, one at point E, one at point F. They are at the middle of each span. Try to consider the collapse load, find out the collapse load using upper bound theorem. Although I did not show you the method, but here I automatically assume that we are using upper bound theorem. I will not ask you lower bound theorem because lower bound theorem just like asking you to do some method. Okay, I don't want to do so in this part. Apply upper bound theorem. That means you have to estimate, you have to predict the collapse load. Collapse pattern. That means the location of plastic hinges and also the number of plastic hinges. 2 things. Where are they in the numbers? We have to ask ourselves how to insert the plastic hinge at some critical positions. But if you have no idea how to arrange the location of plastic hinges, then maybe you may go one step further. You may try to sketch something like the moment diagrams. You may sketch the moment diagram for being under some concentric force. So for example, if you have a continuous beam with concentric force at the middle, then normally you have moment at the location of the concentric force. You have moment at the interior support, right? You have pulling moment, and then you have no moment at the rotor support at the end. You can roughly sketch the moment diagram to see how it's behaving. And from the example as shown at top, you can see that there are a few critical positions we observed. If we have only one force, we observed that we have large moment at the location of the concentrated force. At the same time, you will also have large moment at the interior support. At the interior support, you have Hawking moment. Okay, so it seems that you have a few critical positions: B, E, C. B, C, E, right, something like that. So when you consider the first concentrated force, it seems that you have a few critical positions. Similarly, you can consider the behavior within region CD. For region CD, you have critical positions C and F. D is a hinge. D is a hinge, no moment, free to rotate. So there's no need to consider D. D is already a hinge. So you have two scenarios. The first one is due to portion BC. The other one is due to portion CD. You can consider these two scenarios to see which one gives you smaller value. Okay, and I showed you the configurations and also the location of the plastic hinges. Say for example, for case one. Case one is the collapse occurred between point B and point C. For this case, you have totally three plastic hinges at point B, point C, and point D. Okay, you may think in this way. Originally, everything remains elastic, and when one hinge forms at one end, it's still stable, right? It's allowed you to add one more hinge. After adding two hinges, it's just like a simply supported beam at this region. For simply supported beam, you can add one more hinge to make it collapse. You may also use this idea again, trying to make them become something like a simply supported beam, and then add one more hinge. It becomes collapse. Like here, B, C, and then finally point D. After setting up these configurations, you can find out the collapse flow easily, I think, using up-bound figure. Say for example, this is theta. This side is also theta. Similar triangle. The middle hinge at point E is under rotation 2 theta. Theta, theta, 2 theta. So you can find out the internal work directly. Internal work is equal to 4 theta MP. MP is the plastic moment, assume the same at all sections. External work is equal to the force P time the displacement T, delta. Delta can be calculated using arc length, which is equal to the radius L/2 times theta. So you can find out this equation, eliminate theta on both sides of the equation, and then set them equal. Then rearrange this equation a little bit, then you can find out PC1. I call this C1, case 1. 8 MP over L. If failure occurred within region BC, the corresponding level is equal to 8 MP over L. We do the same thing when failure occurred within region CD. We do the same thing again for this portion. For this case, you can see that there are only two hinges at point C and point F. There is no hinge at point D. Point D is already a hinge at the beginning, free to rotate. So this time in this example, at point F the rotation is 2F and 2 theta. At point C the rotation is theta. The total rotation is 3 theta only. External work is also equal to P times delta. So after simplifying the equation, it seems that for the end span collapse, it only requires 6 MP over L. So we have two critical loads. Which one is more critical? This one. Because when both the loading increase simultaneously from 0, it will firstly reach the smaller value, 6 MP over L. That is the collapse load for this free span beam. So you can see this method is quite not very difficult. For one span beam, for two span beam, we really rely on the same procedures, but just try your best to set up the failure configurations, location of plastic hinge, and then set up the energy equation. Pretty straightforward, this one. No matrix, no differential equations. The following statement, the following paragraph just mentioned that you can continue the analysis based on the collapse load. You can apply structure analysis to find out the other moments, if you like, or the shear force for your desired purpose. But in this module, we just focus on the collapse load, not the following, not the other focus. What about frame structures? In session 1, I demonstrate how to use up-bound theorem on continuous beam. Then what about frame structures? Well, in theory, frame structures, you can also use the same concept for frame structures. Frame structures mean these kind of things. Something like a photo frame, 1 story, 2 story, or even more. You can use the same concept on frame structures. You can estimate the collapse flow rapidly using up-bound theorem. In the past, if you want to use up-bound theorem, or when you want to do loss analysis, it takes you a long time. Right? For frame structures, I asked you this one in assignment 1, question 3. I believe that if you have no Excel, no one can solve for this problem. But you can see that when you use up-bound theorem, everyone can do so, because there's no any matrix. Frame structures. The difficulty of frame structure is that normally it's involve a large degree of static indeterminacy. There are too many reactions, simply speaking. Too many reactions, but too few equations. So normally frame structures involve a large degrees of indeterminacy. And you have different possibility for the structure to collapse. Collapse may occur partially or complete collapse. It may occur on the beam, it may occur on the column, the left-hand side, right-hand side. So you have to try different combinations again. There are many combinations you have to try. Some are new, some may be combined mechanism, and then you have to make some judgment to see which one is more critical. In this part, I will demonstrate how to play with frame structure using a few examples. Before showing the example, I would like to make some conclusions, some common failure mechanism that you will observe for frame structures. Firstly, failure will occur locally on the beam or column. If the beam under concentrated force at the middle, or if the column is under concentrated force at the middle, then you will probably see this kind of local failure mechanism. The beam failure locally with the formation of 3 plastic hinges. We have seen this mechanism many times in this lecture. Normally, if you have this kind of arrangement, 3 hinges, then it becomes unstable. This may also occur in column if you have a horizontal force acting at the middle. In general, this mechanism we call that beam mechanism. The second possibility is that the whole story collapses. If there are totally 4 hinges formed at the column ends, then you can see that when the loading increases slightly, the structure will under relatively large deflections horizontally. This mechanism we call it sway mechanism. Sway mechanism. That means the formation of 4 plastic hinges at the 4 corners that make the structure become unstable in horizontal. We call it sway mechanism. The last one, and also the most difficult one, is called combined mechanism. Combined mechanism means combining the beam and sway mechanism. For this mechanism, you will see hinge at the middle of beam or columns, and then you will see the hinge is formed at the end of columns. It's just mixing the previous two. This one is quite similar to sway. When the force increases slightly, the structure will display with a large amount of values, so it's also unstable. So when you play with frame structures, you may try this kind of combination. You may check the beam mechanism, sway mechanism, and combined mechanism to see which one gives you smaller force. Okay. Actually, the theory remains the same. When you apply upbound figure, you are following the same things. But for frame structures, you have more things to do, more combination to try. Have a look at this example. If we have a rigid frame, not rigid frame, this is one rigid frame with different support conditions. One end is fixed, one end is pin. Point E is a pin support, not fixed. This frame structure is under 2 forces. One is horizontal at point B, the other one is a direct force at point C. 2 forces. One horizontal, one vertical. This is a classical example. You have to check both the basically all the failure mechanism, beam mechanism, sway mechanism, and combined mechanism. Give you 1 minute to have a look at the flow and try to plot the failure mechanism for so-called beam, sway, and combined mechanism. And then we will go through the solution together after 1 minute. The most important thing in this part is able to put down the column mechanism. That means there is a plastic hinge and also the numbers. If you know how to draw the mechanism, I think it's not a big problem. It's quite easy to set up the energy equation. Okay, firstly, we have 3 different mechanisms: beam, sway, and frame. And combined mechanism. You can try all of them to see which one is more critical. So, for example, this frame structure is statically indeterminacy is equal to 2. The statically indeterminacy is equal to 2. How to count static indeterminacy? You can firstly draw the reaction. At the fixed end, you have 3 reactions. At the pin end, you have 2 reactions. So in total, you have 5 reactions. For frame structures, you have 3 equilibrium equations. We have moment equilibrium, we have horizontal force equilibrium, we have vertical force equilibrium. So for frame structures, you have 3 equilibrium equations, 5 reactions, 5 minus 3 gives you 2. So the degree of indeterminacy is equal to 2. According to our theory before, the maximum number of hinges is equal to 3, n plus 1, right? 3. But it doesn't mean always see 3 hinges because you may have partial collapse. So it seems that P equal to 3, but the number of hinges can be 2, okay? The number of plastic hinges can be smaller, depends on the scenario. Anyway, let us consider all combinations. Firstly, mechanism 1. I consider sway mechanism. Sway mechanism means you have hinges at the end of columns. One here, here, here. What about this point? This point is already a hinge at the beginning. Pin support. It's free to rotate. It's a real hinge. Point E is a real hinge. It's not a plastic hinge. It's a real hinge. It's already free to rotate. Based on this failure mechanism, you can try to set up the energy equations. Try to find out the work done. Internal work and external work. Again, you don't need to know the exact rotation. You can select some values. Say, for example, this value. If you assume that this rotation is equal to theta, then the rotation on the other side is also equal to theta. Okay, and then the angle at the top is equal to theta. By doing this geometry, you can find out all features, all rotation angle at all hinges easily. The plastic hinge at point, maybe I do this. I put down the step clearly. The internal work is equal to the plastic work. The plastic work is equal to the sum of all plastic work at all plastic hinges. Maybe I give them some name: A, B, C. The plastic hinge at point A is equal to the plastic moment times the plastic rotation feature. This is the contribution at point A. Point B. The rotation at point B, and you can see the point B. Point B is joining 2 members, one vertical and one horizontal, right? The horizontal member has no any rotation. The vertical member is now under rotation theta. So the total rotation at point B is equal to theta. Theta plus 0, theta. That is the contribution at point B. Point C, I think point C is quite similar to point B, right? The horizontal member has no any rotation. The vertical member is under rotation theta. So the plastic work at point C is also equal to MP theta. External work. External work is equal to the work done due to the external forces. There are 2 external forces. One is horizontal, the other one is 2p. And you can see that for the vertical force, 2p, there is no any downward movement at this point. So 2p has no any work done. 2p has no any work done because you cannot see the corresponding movement. Force P. Force P, you can see the corresponding displacement. there's a horizontal displacement for these total frame structures. Then what is the values? The value of the displacement delta can be obtained using arc length assumption. It seems that the arc length for this part is equal to the height of the structures times the rotation theta. The height of this structure, 2L. So force times delta. Delta is equal to 2L theta. Something like that. In the solution, I directly set external work minus internal work equal to 0. I just express in the other way. Okay, instead of setting their equal, here I consider their subtractions. Actually, the same thing, right? Eliminate feature, and then you can simplify the equation a little bit. You can see that for mechanism 1, the collapse force is equal to 3 MP over 2L. Just redo the things for case 2 and case 3. You have beam mechanism, you have combined mechanism, 2 more. Beam mechanism. I think beam mechanism is quite easy because it's just like a one-span beam. For beam mechanism, mechanism 2, you have totally 3 hinges at the 2 ends and at the middle. If one side rotation is theta, the other side also equal to 2 theta. The middle rotation, 2 theta. So for beam mechanism, it's just like what we did before. But one thing is that this time, the horizontal force has no any breakdown because there's no any horizontal displacement for beam mechanism. We have only direct displacement at the middle. So after simplifying these expressions, you can get 2 MP over L. This part is just like the fixed end beam that we considered before. Okay, no new things. So you have the other collapse law, PC, for case 2. The last one is combined mechanism. Normally, combined mechanism is the most complicated one. Combined mechanism is the most complicated one. For combined mechanism, one hinge form at the location of the direct force, just like a beam mechanism, and the other hinges will form at the column ends. Here is my arrangement: one at the middle of beam, the other at the columns on the left and on the right. This corner on the right-hand side, this corner, there is no any plastic hinge at the top left-hand corner, so this left-hand corner remains right angle after bending, because there's no any plastic hinge at this corner. We ignore all the elastic diffractions, so this corner remains right angle. This one one conditions. So right here, if the rotation at the bottom left is theta, if the rotation is theta, the rotation at the top is also equal to theta because this is a right angle. Okay. The other side, the other side is equal to theta. Why the other side is equal to theta? Actually, we have one thing we assume. We assume that displacement here and the other side are the same. We assume that these frame structures have the same horizontal displacement on the two sides. Okay, we assume that they have the same displacement on the two sides. So if the left-hand side is theta, the right-hand side is also equal to theta. Theta, this one, theta. So we have sufficient information for our calculations. Say for example, plastic work. Maybe I give them some name, A, E, and C. You can see that the plastic work at point A is equal to MP times theta. This is contribution at point A, plus the contribution at point B. At point B, the plastic work is equal to plastic moment times the total angle rotated at point B, 2 theta, right? 2 theta. Because the left-hand side is theta, the right-hand side is theta, theta plus theta give you 2 theta. Plus the contribution at point C. We have 3 hinges. The last one is at point C. At point C, the plastic work is equal to the plastic moment times the total rotation at point C. Point C is joining 2 members, horizontal and vertical. You can see that the horizontal member is under rotation theta. The vertical member is under also rotation theta. Theta plus theta. So the total rotation for plastic hinge C is equal to 2 theta. This is the contribution at point C. Okay, so the total rotation, when you take a look on the solution, the total rotation is equal to 5 theta at point A, point B, and point C. Breakdown. For breakdown, you just evaluate the corresponding displacement. Here you have delta. Maybe I call this delta H, delta horizontal. And here you have delta V, delta vertical. We have horizontal displacement and vertical displacement this time. So both external forces will have breakdown. Both external forces have breakdown because you have 2 displacements this time. Delta H horizontal and delta V vertical. Delta H, we mentioned it in mechanism 1. Delta H is equal to 2 L theta. We just mentioned in the previous mechanism here. Delta V, we mentioned it in mechanism 2. So you can see that combined mechanism is not always new. It's not totally new. It is something that you can copy from the previous mechanism, and that's why we call it combine. But it's not more lengthy, so you may need to take longer time to simplify these expressions, slightly longer time. And then after this cancellation, you can find that the collapse load is equal to 5 MP over L4. So we have P1, P2, P3. P1 is 3 over 2. 3 over 2 is just like 1.5, right? 1.5 MP over L. And then you have this one, 2. The coefficient is 2. The last one, the coefficient, this one is smaller, right? This one seems like the smallest value among the three numbers. So it seems that case 3 is our possible covariant mechanism, and so the collapse load is this one. You just pick the minimum values. Find out P in. Okay. For frame structures, you just need to consider that 3 failure modes: combined mechanism, beam mechanism, split mechanism, and combined mechanism, and then compare which loading give you the minimum values. This is actually not an example. I just want to illustrate that for frame structures, you may sometimes handle some frame structures with inclined member. In this section, just talk about how to handle inclined members. Next time in our tutorial sections, I will give you an example with numbers, how to dealing with this kind of complex problem, frame with inclined members. You can see that we have two fixed n. On each fixed n, we have three reactions, and we have two inclined members. We have two different forces, P and Q. In total, we have 6 reactions. We have 3 equations. So it seems that our degree of impermanency is equal to 3. It seems that the maximum number of cross hinge is equal to 4. 4 hinges if you consider only the complete collapse mechanism. 4 hinges. How many critical points we have? It seems that we have maximum at the corner, right? A, B, C, D, E may have plastic hinge in this neighborhood. 4 hinge make the structure collapse, but you have 5 possible positions. That means you have to use try and error again. You have to try any combinations. Say, for example, you assume that you may have hinge at point A, C, D, E. You do the upper bound preview, and then once you finish, you try and other combinations. Maybe I just arbitrarily pick some positions. A, B, C, D. We do the things again and repeat this process until the one that gives you minimum combinations. So even for these relatively complex structures, you can also use the same idea upper and inferior. Just set up the collapse mechanism and then find out the collapse load using energy concept balance. Okay, this is only one possibility. You may have possibility 2, 3, 4, and 5, etc. You have to try all things. In the tutorial sections, I will have one example like this. We will work with it to see how to deal with this one with 2 different values of loadings, P and Q. Before closing this section, I will give you some tips here. When you're dealing with inclined member, when you want to deal with inclined member, you have to be aware of the geometry, because when you consider inclined member like this, when you use arc length, equations, you actually consider this component, the component perpendicular to the member here. When you use arc length, actually this is the corresponding displacement. L times theta. Theta is the possible rotations. L is the length, the radius, right, of the circle, imaginary circle. You can see that the displacement is in inclined directions. The displacement is in inclined directions. But in our analysis, we normally consider horizontal and vertical. We seldom consider inclined directions. So here, you can resolve this diagonal component into the horizontal and vertical component. How? You can use trigonometry, sine cosine. Say, for example, this vertical component is equal to L theta cosine alpha. The horizontal component is equal to L theta sine alpha. Using sine cosine, with the angle alpha, you can project this diagonal back to horizontal and vertical components. So that when there is force, suppose there is force right here. If there's force acting at this point, the force times this diameter displacement give you the corresponding work done. Okay, you can use this concept to calculate the displacement along vertical and horizontal component. You can further simplify these expressions. Instead of using sine cosine, you can see that L cosine alpha. When you consider this triangle, L cosine alpha means what? L cosine alpha means the distance A here. L sine theta means the height of this right angle triangle. So when you read the expression here, I use B theta instead of L theta sine alpha because I found that L sine alpha is equal to B. Why we have these expressions? Just make our calculation more easy. Say, for example, if you want to know the diameter displacement of an inclined member, if you want to know the diameter displacement at the inclined member, the calculation is quite straightforward. It's just equal to the plastic rotation theta times the distance perpendicular to the direction under considerations. Say, for example, if you want to know the diameter displacement, then the calculation is equal to the horizontal distance A times plastic rotation theta. Similarly, if you want to know the horizontal displacement, the calculation is equal to the vertical distance perpendicular to the direction under consideration, right? B times the plastic rotations. You can use this shortcut to evaluate the vertical or the horizontal displacement of an inclined member. Okay, the shortcut. Actually, they come from trigonometry, sine cosine. In the problem, you normally under downward force and horizontal force, so you need to know how to find out the downward and horizontal displacement. This slide just shows you some tips how you can evaluate horizontal and vertical displacement using this short form. Otherwise, you have to always project yourself. It may take you some time to do so. And finally, you can set up the energy equations. You can set up the energy equations to find out the correct law. But it's not easy because you can see that we have different rotation angle, theta, phi, alpha. Quite often, you have more than one rotation angle for rigid frames with impounded members. Next time, I will show you some skills how to deal with frame structures with more than one angles. Actually, I've shown you already. If you have more than one angle, then what you have to do? You find out some common displacement. Say, for example, you can consider displacement F upon C. The diameter displacement F upon C can be expressed using member BC and member CD. By correlating these two angles, by using this common displacement, you can correlate these two angles. Next time, I will demonstrate how to play with this kind of calculations. Since we would like to know the effect due to axial force and due to shear force on the behavior of plastic hinge. In section 1, in topic 10, topic 11, we basically focus on beam in bending only. Beam in bending means we have a beam without any axial force, just have the bending effect. But in reality, say for example, when you're dealing with columns also under shear force, under axial force, it may affect the plastic capacity of a beam. Right? For pure bending, you can draw the stress profile easily. I believe that all of you know the stress profile for a beam under pure bending at the fully plastic stage, all section yielded in tension or compressions. But what happens if there is also axial force or shear force acting on the same sections? That is the idea we would like to know in this particular section. I go to some picture first before moving on to discussing this paragraph. I think the picture can explain more easily. Say for example, if we have a section just like a column sections under axial force and under bending moment, we have M, we have P, so it will affect a little bit on the stress profile. Say for example, if we have bending moment, it will induce bending stress. Bending moment induce bending stress. Axial force induce some normal stress, SO stress, along the whole sections. If you still remember in mechanics materials, when a member under bending, it will induce bending stress, something like this. When a member in axial force will make the member under uniform compressive stress. When you superimpose the two stress profile together, you can see that the resultant stress profile is no longer symmetrical. Right? The zero line is not at the middle. It will be below or above the middle point of the beam section or the column sections. That is the effect of axial force on the cross sections. So that when you integrate the whole stress profile, it will give you one force, which is used to balance the external axial force. Okay, that's why the stress profile will be slightly different from the one that you saw before in topic 10. Okay, not in pure bending. Again, when the loading increased gradually, at the beginning, everything remained elastic. Nice. But when the loading increased gradually, one extreme fiber will start to yield first. The other side remain elastic, but one side will yield first because it's not symmetrical right now. One side is under high stress level. This is one condition that we would like to know. Just yield condition, right? The members start to enter the yield stage. So this is also one interesting phenomenon we would like to know. Okay, I'm going to start here. When the loading increases further, partially yield, partially elastic. This is so-called a transition state or elastoplastic state. Something that we are not really interested in. When the loading increases further, the bottom side is also yield. The top side yield. The middle part remain elastic. Remain elastic means it's still able to take some extra loading. So when you finally increase the loading, the final stage will be like this. You have two rectangular stress blocks, one bigger, one smaller. This is another special situation we would like to know. Fully plastic condition, something like that. The whole section yielded. But the rectangle here are not identical. One is bigger, one is smaller. So that when you calculate the resultant force, it will give you one force equal to the external axial force. Okay, force equilibrium. So one big, one small. We would like to know these two special situations with a star, but just you and fully plastic. When I go back to the previous slide, I just mentioned the thing that I just discussed using picture. The stress profile is not symmetrical, one side bigger, one side smaller. But this time we have two parameters, something like that. We have axial force, we have bending moment. So normally we will express the combination of bending moment and axial force using some form of interaction formula. Actually, you have seen this before when you learn ROC design. When you learn ROC column design, you use something like the design chart. You use design charts, right? ROC column design. ROC design chart actually is some interaction formula, interacting between axial force and bending moment. We want to know two special situations. Onset of yielding means just yield condition. Right? The first star I showed you on the next slide. And fully plastic conditions mean fully plastic, whole section yield. You can derive the formula to describe the onset of yielding conditions and the fully plastic conditions. This page, we focus on onset of yielding. That means scenario 1. If you want the section remain elastic under the actual performance, then you may use this as the failure criteria, onset of yielding. If you don't want any fully plastic condition occur, then how to derive the failure curve for onset of yielding? Using the previous concept, you can calculate the bending stress due to the bending moment. We have discussed in topic 10 already. I showed you how to derive the fracture formula. Something like that. Right. Similarly, when the member under axial force induce normal stress as well, the value is equal to P over A. So when you want to know the stress on the extreme fiber, it seems that both effects will give you compressive stress or tensile stress. It seems that it will give you the highest level of stress. So you can add then up, it becomes this formula. I use N for axial force, I use M for moment on my slide. If you want to understand the just yield phenomenon, then you can set the resultant stress equal to the yield stress. Okay, and then divide the whole equation by yield stress. Regroup the denominator to a constant, to a term called capacity, axial capacity, moment capacity. Then you have one so-called interaction formula. Oh, there's some typo. This is not fully plastic. This is onset of yielding. This interaction formula, N over N0, N0 is here, plus M over M0 equal to 1. This is the interaction formula for onset of yielding. That means if any combination of moment and actual force meet this equation, if any combination of m and n meet this equation equal to 1, that means the member will enter the just yield condition onset of yielding. Okay, you will start to see some yielding on the extreme fiber. In case if the loading such that the combination of n and mn less than 1 means yielding does not occur. Okay, no yielding. So this equation gives you the criteria under what condition you will see just yield, under what condition remain elastic. A very useful interaction equation. Using similar principle, if you want to know the fully plastic conditions, using similar principle, you can also find out something like the interaction formula, but in a more complicated form. For fully plastic condition, you have the stress block, something like that. If you want to know the total force, actual force, then you can find out the resultant force for the compression, for the tension, and then add them up together. It will give you one resultant force, something like that. I will not ask you how to derive the formula, don't worry. So here I just give you the outcome. The total actual force, C minus T, give you this expression. If you have time, you may verify yourself. Moment, how to find the moment? You have the moment arm, you have the actual force, then taking moment, it will give you the moment. Right? Combining these two equations together, then you can set up the interaction formula. I give those derivations, I just give you the outcome directly. We can see that this formula is a square. A square means this equation is not a straight line. This equation is something like a parabola. Similarly, any combination of m and n meet this equation will make the structure enter the fully plastic conditions. You will see a full stress block. Okay. We can understand this graphically. I plot the two equations on the graph. The y-axis is the normalized actual force, n over n0. The x-axis is m over m0, the normalized moment. I plot it on the graph, and you can see that the blue line represents onset of yielding, the red line represents fully plastic conditions. So you can understand using this kind of graph. What I mean is that any combination of m and within all curves, just like here, they are safe. Safe means they are not yield, right? They are not yield. If any combination of m and within this area, there are no yielding, no plastic, everything remains elastic. In case if the combination reach the blue line, means you will start to enter the yield state, right? The onset of yielding conditions. It may be here, it may be here, depends on the combination of m and in your situations. But in theory, the member is still able to take some extra loading, right? Onset of yielding doesn't mean failure. So in theory, you may also increase a little bit to the red line. When the member enters this red line, what I mean is that if the combination reaches red line, which means fully plastic condition occurred. One fully plastic condition occurred, the member, is cannot take further loading. Right? It is the maximum capacity that can be taken by this member with the consideration of moment and actual force. In theory, no combination can exist outside this graph, right? Because fully plastic conditions, all sections has been yielded. So in theory, you cannot go further. So this is the meaning of this interaction graph. Quite useful to understand the behavior between actual force and moment. Shear, effects of shear, I just go through roughly because the shear phenomenon is much more difficult to predict. But normally, for when you consider ROC design or steel design, normally we use rectangular beam or I beam. So here I just show you the curve for these two particular cross sections, rectangular sections and I sections. I plot similar graph. One axis is the normalized moment, the other axis is normalized shear force. We talk about shear force right here. On the graph, you can see that when the shear force is small, just like here, when the shear force is small, if the shear force is small, it seems that the effect of shear is very little. Right? This line almost remains horizontal, which means that the moment is, when failure occurred, it's basically governed by the moment. Right? The moment equal to the capacity m0. Shear force has not much influence on the moment behavior, so the strength remains horizontal. Right? You can keep the fractional strength. That is true for I-beam, for rectangular beam, when the shear level is small. Normally, we consider small shear in our design for normal beam. But in case when shear increase, you can see that there is some effect on the moment capacity. Moment capacity starts to decrease when shear force increase. But this phenomenon more significant for rectangular section. For rectangular section, the effect of shear force is more significant. But for I-beam, it seems that for I-beam, the effect is also not very significant, unless the shear force is very, very, very close to the capacity. So in practice, normally you can ignore the effect of shear force when you're dealing with some reasonable shear force. So after going through the effects of actual force and shear force on the plastic hinge, we found that actual force and shear force will affect the moment capacity a little bit. Right? Using interaction formula, you can find out the relationship between actual force, moment using interaction diagrams. For shear force, we realize that for low shear, there is not much effect on the bending capacity. What about the last part? The last part, section 4, I turned that to reference. This is not for examination. It is some reference material for you to enrich your understanding. The idea of this part is pretty straightforward. In the previous sections, we introduced upper bound theorem, lower bound theorem for frame, for beam. Beam and column, there are some straight line elements, 1D elements. Beam and beam are some 1D straight line elements. You can use upper bound theorem or lower bound theorem to analyze the collapse law. But in fact, you can also extend this upper bound, lower bound theorem to 2D element as well. But not only 1D. This kind of theorem can be also applied on 2D element, just like slab. Euler method. Euler method, you can think this way. Euler method is upper bound theorem in 2D versions. What is upper bound theorem? In topic 10, we learned that upper bound theorems mean we consider the collapse mechanism, failure mechanism, and then based on energy, you can estimate the collapse law. For beam, plastic hinge locate as one concentrated point. Then what about for slab? For slab, when yielding occurred, for slab, it will appear as a straight line, not a point, but a straight line. We call that U line. For 2D version, the plastic hinge is not a point, right? It's a straight line. That's why we call that U line method. The U line pattern depends on the boundary conditions, how many support you have. But in general, if you have one failure mechanism, you can, based on this failure mechanism, set up the virtual work equation. The left-hand side is the work done, is the energy dissipation along the U line. The right-hand side is the external work done. You can see that the calculation is much more complicated for 2D slab. That's why I turn this part to reference, because it involves some relatively complex calculations. But in terms of concept, you see that it's the same as 1D, just the calculation more complicated. Upper bound theorem based on failure mechanism, but for 2D version in a straight line form. Then what is lower bound theorem? Lower bound theorem, on the other hand, we consider equilibrium conditions. Based on the equilibrium conditions, based on the moment diagram, you can work together with the U conditions to find out the collapse law. We introduced in topic 11 already for B. For slab, you can also follow the same way. But for slab, the equilibrium equation for slab will be much more complicated, something like this. Partial differential equations. And that's also the reasons why I'm not going to assess it in examinations, because it's so complicated. Okay? But in theory, again, lower bound theorem based on the U criteria and also equilibrium. If you have some way to solve for this equation, then you can also use lower bound theorem for slab. Okay? Just let you know something outside the scope of the syllabus. Instead of 1D, actually the principle of the principle of plasticity can also apply on also 2D slab, not only for 1D. If you want to learn more, you may have a look at the textbook. Okay, this is the end of this topic. This is the last topic of this semester.